Suppose a sub 1, a sub 2, a sub 3, and so on is a sequence defined as follows. A sub 1 equals 1, a sub 2 equals 3, a sub k equals a sub k minus 2 plus 2 times a sub k minus 1 for every integer k greater than or equal to 3. Prove that a sub n is odd for every integer n greater than or equal to 1. We're going to use strong mathematical induction to prove this statement. We'll start by identifying the predicate p of n. P of n is going to be the predicate that a sub n is odd. We don't want to include the universal quantifier in our predicate. And that's because if you combine this universal quantifier with the predicate portion, then you end up having a statement. And P of n is not a statement, it's a predicate. And the truth value of P of n is determined by the value of n. Now, the reason why we have to use strong mathematical induction is because we will be using this recurrence relation in our inductive step. And in this recurrence relation, there is a relationship between a term and its prior two terms. This says that a sub k equals a sub k minus 2. That's not the term before a sub k, but two terms before a sub k. And then plus 2 times a sub k minus 1. That's the previous term. So a sub k depends on the prior two terms. Now, with strong mathematical induction, we need to start with the base case. The number of base cases that you need to prove is determined by the gap between the largest subscript and the smallest subscript in your recurrence relation. That's usually the case. But more specifically, it's because we are going to be using a recurrence relation where a sub k depends on the prior two terms, and we'll be using this in the inductive step. Since we have to prove P of n is true for all integers n greater than or equal to 1, then that means that 1 is the smallest integer such that P of n is true. Since we need to prove two base cases, that means we need to prove that this predicate is true for n equals 1 and n equals 2. We'll start by proving P of 1. We want to show specifically that a sub 1 is odd. Now, I'm going to put a question mark here because we want to prove this to be true. We don't want to assert this to be true. So by putting a question mark there, I'm not asserting any truth values here. I'm just wondering if a sub 1 is odd. Well, we know that a sub 1 equals 1. That's given to us here. And 1 is odd. Now, how do we know it's odd? I know it's kind of a silly question because we're taught that it's odd. How do we know that this is odd? Well, it's because 1 is equal to 2 times 0 plus 1. Every odd integer can be represented of the form 2k plus 1 for some integer k. In this case, the integer k happens to be 0. So by this definition of an odd number, 1 is an odd number because I can find an integer k such that 1 equals 2k plus 1. So I'll put a check mark here to show that we have proven that a sub 1 is odd. Now we have to prove that p of 2 is true as well. P of 2 says that a sub 2 is odd. I'll put a question mark there to avoid the assertion of any truth. Now by the given, we have this a sub 2 equals 3. So we know that a sub 2 equals 3. And 3 is an odd number. But how do we know it's an odd number? The reason why 3 is an odd number is because we can write it as 2 times 1 plus 1, where this 1 here is an integer. And so that integer is the k from the definition of an odd number. And so we have verified that a sub 2 is an odd number. So now we're going to get to the inductive step. For strong mathematical induction, the inductive step looks very different than normal mathematical induction. I'll start by saying let k be a fixed arbitrary integer. I imagine k as a sort of like number behind a curtain. There's some number there, that number's not changing, but k as a letter acts as a curtain that covers what that number is. We don't know what that number is, but that number doesn't change, whereas a variable varies. K is not a variable in that sense. So let k be a fixed arbitrary integer, and now this is the part where strong mathematical induction gets a little weird. We're going to let k be greater than or equal to 2. Normally, we let k be greater than or equal to 1, which is usually the base case. But in this case, there are two base cases. We're going to let k be greater than or equal to the very last base case. And we're going to assume that P of I is true for all 1 less than or equal to I less than or equal to k. This is the part of strong mathematical induction that a lot of students feel uncomfortable about, which I totally understand. I remember first looking at this when I took discrete math, and I was kind of confused by this part. Let me explain what's really going on here. We're assuming that P of 1 is true, and we're assuming that P of 2 is true, and we're assuming that P of 3 is true, and so on, all the way up to P of k minus 2, P of k minus 1, and then the very last term, P of k. This is what we're assuming. Now, keep in mind, we don't really know what k is. All we know is that k is greater than or equal to 2. I'm kind of assuming k is greater than 6. This picture doesn't make sense if k is like 2, for example, because when k equals 2, we would only be assuming that P of 1 and P of 2 is true, and that's it. I like to write out multiple terms, though, because we are going to imagine k being very, very large, and it doesn't really matter what k is. We're always going to end up showing that P of k plus 1 must therefore be true. And that's sort of the long-term goal here, is that by assuming all of these things to be true, we're going to prove that P of k plus 1 is true. In normal mathematical induction, we only get this P of k as a tool to help us prove that P of k plus 1 is true. Strong mathematical induction is stronger in that you don't get to just assume that P of k is true. You also get to assume that P of k minus 1 is true, and P of k minus 2 is true, and all the way down to P of 1, which is the base case. You get to assume that all of these are true, and you get to use all of these tools to be able to show that P of k plus 1 is true. We're actually not going to need all of these things to prove that P of k plus 1 is true, but in strong mathematical induction, it's important to see that all of these things can be used to show that P of k plus 1 is true. For us, we're only going to need P of k and P of k minus 1. We'll actually not need any of the other P of i's because we can just use P of k minus 1 and P of k to show that P of k plus 1 is true. That's only for this proof, and that's kind of what makes this strong mathematical induction a little bit easy. Let's go back to P of n. P of n is the predicate that a sub n is odd. Since P of k is true, this means that a sub k is odd. And since P of k minus 1 is true, that means that a sub k minus 1 is odd. So now we have to ask the question, is a sub k plus 1 an odd number? That's what we want to show. We want to show that a sub k plus 1 is odd. I put like a little question mark there so that we can ask ourselves, is this odd? And if so, why? Hopefully the answer is yes, because then that would mean P of k plus 1 is true, and that's a crucial thing we need in strong mathematical induction to prove that P of n is true for all n greater than or equal to 1. Now, what do we know about a sub k plus 1? Well, we have a recurrence relation given to us at the very beginning here, which says that a sub k equals a sub k minus 2 plus 2 times a sub k minus 1. Now, this is a statement about a sub k, but we want to make a claim about a sub k plus 1. But keep in mind that this recurrence relation holds for each integer k greater than or equal to 3, which means that the k in this recursive definition is a sort of temporary variable that's universally quantified, meaning that k can be anything so long as it's greater than or equal to 3 and it's an integer. So that means that since this is true for all k greater than or equal to 3, then we can apply that recurrence relation to a sub k plus 1 since k plus 1 is greater than or equal to 3. Keep in mind, k is greater than or equal to 2, so if you add 1 to both sides of this, that would show that k plus 1 is greater than or equal to 3, and since k plus 1 is greater than or equal to 3, then we can apply the recurrence relation to a sub k plus 1. So that means that a sub k plus 1 equals a sub k plus 2 times a sub k minus 1. So that means that a sub k plus 1 is equal to a sub k minus 1 plus 2 times a sub k. I'm taking the recurrence relation and I'm shifting the indices by 1 unit. And let's clarify why this is true. This is by the recursive definition. But now we can utilize our inductive hypothesis. We know that a sub k minus 1 is odd, and we know that a sub k is odd. That means that both of these numbers here are odd. Since a sub k is odd, then a sub k equals 2 times L plus 1 for some integer L. And we know this by the inductive hypothesis. We can make the same claim about a sub k minus 1 being odd. And we'll say that a sub k minus 1 equals 2 times S plus 1 for some integer S. We're using a different letter here just so that we ensure that a sub k minus 1 and a sub k aren't necessarily the same numbers. They might be different odd numbers. So now let's go back to this recurrence relation. A sub k plus 1 equals a sub k minus 1 plus 2 times a sub k. We can use substitution. So this will be a sub k plus 1 equals a sub k minus 1, which is 2s minus 1, and then plus 2 times a sub k, which is 2l plus 1. And now we have something to work with a sub k plus 1. We could do a little bit of simplification by distributing this 2, and we can also drop these parentheses here to get 2s minus 1 plus 4l plus 2, which is equal to 2s plus 4l plus 1. I have a plus 1 here, which is pretty convenient to prove that this is an odd number, because now we can just factor a 2 out from all the other terms, which will give 2 times s plus 2l plus 1. Now what's important here is that s plus 2l is an integer, and that's because integers are closed under addition and multiplication. And so now we can say that a sub k plus 1 is an odd integer. And that means that p of k plus 1 is true. A sub k plus 1 is odd because a sub k is odd and a sub k minus 1 is odd, and because of that recurrence relation. So now we can conclude this proof with, by strong mathematical induction, p of n is true for all n greater than or equal to 1, all integers. So now we can conclude this proof with, by strong mathematical induction, p of n is true for all integers n greater than or equal to 1. Thanks everyone, and I'll see you in the next video.